Hello everyone, I am Chris, and in this video we'll be going over the implementation of a genetic algorithm in C#. I will briefly explain the structure and the concepts behind genetic algorithms, but will not go too in-depth. There's already plenty of videos that do that very well. I will put a link in the description to one of the best I've seen. We'll be using the Unity game engine to demonstrate the algorithm in action, but the implementation will be as generic as possible. We will not use anything that's specific to Unity, just C# native stuff. So hopefully you'll be able to use this on any C# application, be it Unity, Monogame.net or whatever, unless, of course, I made a mistake, which is entirely possible, so please let me know in the comments if that's the case. We will even use C# generics, and if you don't know what that is, don't worry about it, it's pretty easy to understand after seeing it used. I will also give a brief explanation, and in any case there will be a link in the description for more info. So, what is a genetic algorithm? It's an artificial intelligence algorithm inspired by the process of natural selection and evolution. How does it work? Well, how does evolution in real life work? First, we need a population of something, a species of animal or plant. Each individual of that population has genes. Through natural selection, the fittest members tend to survive longer, meaning that they have a higher chance of reproducing. Their genes get carried over to their children when they reproduce, and when a new individual is born, there's also a chance that a mutation might occur, which means that one of their genes is changed to something new, something that didn't exist in either of his parents, and by repeating this whole process over and over again, the overall fitness of the population improves over time, and this is what is called evolution in very general terms. But what does this mean in programming terms? So a population will simply be an array of individuals, which is a class that we will create. Individuals are represented by their genes. Their genes are an array of a certain kind of data type. It could be an int, it could be a float, boolean, char, just some custom class that we make. It can be anything, really. Natural selection will be a function that we're gonna implement to calculate how fit each individual is. Reproduction is the process of obviously creating a new child from two parents. In genetic algorithms, that is commonly referred to as crossover, where the genes of one parent cross over with the genes of another parent to create the child. And also mutation, which is, as we said, is simply a random chance that one of the genes of the newly created child will be changed at random to a new one. As a quick demonstration, which I sort of stole from the video I said I linked in the description, there's a thought experiment that states, if you had a room filled with thousands of monkeys, all of them typing completely random things on their keyboards, and if you had an infinite amount of time, eventually those monkeys would have typed the complete works of Shakespeare, just through sheer luck. As you can imagine, that would take a ridiculously long amount of time. And even if we were to narrow it down to just the phrase to be or not to be, I believe the math works out that it would still take longer than the age of the universe. But don't quote me on that. So let's be a little smarter about it and try to evolve our monkeys through a genetic algorithm. We'll start out with a completely random set of phrases. For each generation, we will evaluate how close each phrase is to our target, and the best phrases will reproduce, in quotes, the most. That means that eventually we will be able to reach our target phrase, and a little bit faster than the age of the universe. Hopefully. Okay, so let's jump over to Unity and see how this all works out. I'm just gonna hit play and pause right at the start. So on the right here you can see the list of phrases that were randomly generated, and they're not really phrases right now, they're just a bunch of random letters and symbols. On the left you can see the target phrase that we want to achieve. Under it is the best phrase of the current generation, and under that is the score that we're assigning it, which relates to the natural selection part of the algorithm, which is essentially just assigning a score to all elements of the population. And under that, the current number of the the current generation we're in. I'm just gonna unpause this and you will see these phrases gradually start to change and resemble our target more and more, and until it finally stops and achieves its goal. So we were able to get to the phrase to be or not to be in 45 generations, not bad. Alright, let's see how to actually implement this. We'll start by creating the class that represents the individuals of our population. I just called it DNA because it's short and I feel it gets the meaning across well enough. So the first thing that we need for this class is going to be the gene array. But what exactly is the gene array? As we said, it could be of type int, it could be char, it could be float, it could be really anything. So how are we gonna deal with this? Well, we don't really need to know the type in advance in order to deal with it, and this is where C# generics come into play. So what we can do is write it just like this, and this is exactly the sort of thing that you do when you want to make, for example, a list, where you just say list, and then inside the lesser than and greater than symbols you tell it the type of object that you want to store. And we actually need to also tell it to use this namespace. And by the way, this is exactly why this namespace is called collections generic, because these collections use C# generics in order to be able to store any type of data. So we don't actually need this. Let me get this out of the way. So our gene array is going to be of type T array, where T represents any arbitrary type that we want to store. And this way we can simply have a generic DNA class that can deal with any type of object that we need. And I'm just gonna declare it like this, so that it's accessible from the outside, but we can only change it from within this class. We will also need to store the fitness of each individual. As for the constructor, we will need to give it the size of the gene array and create the gene array with that same size. So there were three main phases to the genetic algorithm. The first one was the natural selection part, which in programming terms just means calculating the fitness of the individual, which is basically just a score, which we will then use to decide how likely that individual is to reproduce or not. And since we don't know what the fitness function is right now, we will just leave it at returning 0 for now. The second phase was the crossover, which returns a new object of type DNA by joining this object with another one, because obviously reproduction requires two parents. And the third part was the mutation, which needs to know how likely it is to mutate each gene. For the crossover, we know we want to generate a new object of type DNA, which we will call child, and his gene array size will be the same length as his parent. So what we want to do now is combine the genes of his parents in order to generate his genes. To do that, we will want to go through the genes of the child, and we will essentially want to flip a coin. If it lands on heads, it will grab the gene of the first parent, and if it lands on tails, we will want to grab the gene of the other parent. And how do we flip a coin? We need to first import the system namespace, and then create an object of type random. So we will use this object to generate a random number between 0 and 1, using the function nextDouble. And if this number is less than 0.5, then we will use the genes of the first parent. Otherwise, we will use the genes of the second parent. Lastly, we will need to return the child. However, we are doing something really bad here. We are creating a new object of type random every time we run this function. And this is not only bad in terms of memory and garbage collection, but also creating new objects of the random type within a short period of time will actually make it so that the sequence of numbers they generate is the same, which completely defeats the purpose of wanting random numbers. In order to fix that, we will pass in as an argument to the constructor an object of type random, which we will create only one instance of somewhere, and store it in here and keep reusing the same one instead of creating new ones every time. And we also need to give it to the new child as well, of course. For the mutation, we want to go through each gene and basically check if it's going to suffer a mutation or not. And to do that, we will generate a new random number. If it happens to be lower than the mutation rate, then we will assign it a new random gene. But how the hell do we do that? How do we generate random objects of type T? Well, we don't know. So let's ask somebody else to do it for us. We will declare a variable of type funct called getRandomGene, and what this essentially means is that it stores a reference to a function that returns an object of type T. It's a variable that holds a function, something like this, something, return something T. And this implementation is obviously not correct because T is not a real type, but we don't really need to care about the implementation of this function right now. What matters is that we will trust that this function will actually generate a random object of whatever type this happens to be. We will need to store this function in here and assign it, and also pass it to the new child as well. And in here we are going to use this function to generate a random gene. However, to start with, the genes of each DNA should be random, so let's also use this function to do that. We will go through the gene array, and for each gene we will generate a new random gene. But there's a small detail here regarding this initialization and the crossover. We are initializing the genes of each element when we make a new one, which will happen here, but then right after that we are just assigning new values to it. So maybe we don't need to do this every time. Let's declare a boolean here called shouldInitGenes, and we will give it a default value of true. So we will only do this initialization if it should init genes. Right down here in the crossover, we will tell it that shouldInitGenes should be false. This way we don't waste time generating random genes when we are just going to replace those values anyway. And while we are on the topic of storing functions in variables, if we think about it, the calculateFitness function is actually something this algorithm can't possibly know. So it's probably a good idea to do something like this for the fitness function. Let's declare another variable of type func. This time it will return a float, and it will take in as an argument something of type int, and this variable will be called the fitness function. We will also need to store it out here and assign it in the constructor, and inside the calculateFitness function we will use this fitness function that we gave it to actually calculate the score and return his own fitness. But we said the fitness function would require as an argument a parameter of type int, so let's do something like this. And while this index isn't really doing much right now, it's really gonna come in handy later when we actually implement this fitness function. And once again we will need to fix the constructor here to receive the fitness function as well. And I believe we are done with the DNA class, so let's hop over to the main genetic algorithm class. This will also need to be generic, and for the most important part of this class, it's going to need to store a list, for which it needs the system collections generic namespace. And this list will be of type DNA T, and it will be the population list. For now, this could very well be an array instead of a list, but it will save us a little bit of time later if we declare it as a list right now. So let's do that. And I'll also add here an int that's going to be the generation number, so that we can see how many generations have passed. we will need to store the mutation rate. And the reason I'm not declaring this as private set is because I think it's actually quite interesting if we can change the mutation rate while the algorithm is still running. And similarly to what we did here, we're going to need to store a private random for the constructor. This will need to know the population size, the size of the gene array for each element of the population. It's going to need to receive the random and the getRandomGene function, and also fitness function, which I will just copy from here. Oh, and we still need to give it the initial mutation rate, which I will give a default value of 0.01 because it's a pretty common and used value. It's not too much random and not too little random either. So to start with, we will start at the first generation, of course. The mutation rate will be set to the initial mutation rate, and we will need to initialize the population and also assign the random object. And we will need to actually create the elements of the population. Population.add, creating a new DNA type T, the correct DNA size, the random object, getRandomGene function, fitness function, and should init genes true. The main thing that this class is actually going to do is continuously generate the new generations. We'll create a function called newGeneration, and just as a safeguard, if the population size is actually 0, then we will simply return out. And the first thing, again, the 3 phases of the genetic algorithm, we will need to calculate the fitness of all the individuals of the population. So let's declare a function that does just that. We don't know what it does yet. We need a list to store the new population that we are making. And the second phase is the crossover. But how are we going to crossover? We will need to generate as many individuals as there were in the last population. So we will do a for loop until the size of the population. And we will also need 2 parents that will be performing the crossover to generate the new child. However, we don't really know how to select the correct parents because they must be chosen based on their fitness, so we will leave it at that for now. The child will be the result of first parent doing the crossover with the second parent, and of course it's giving me errors because these haven't been assigned. Let's just put it like this for now. It will obviously not work, but just so we don't get errors. And for the third and final phase of the genetic algorithm, we will need to mutate the child according to the mutation rate. And now that we have our new individual, we will actually need to add it to the population list that we created earlier. And after we are done creating all the new elements, we will simply say that the population will be the new population. And also, must not forget, to increment our generation counter. Calculating the fitness should be fairly easy. We will need to go through our entire population. For each individual of the population, we will just call his fitness function, giving it his index on the population list. And now, let's see how we can create a function that will select a parent based on his fitness. We will need to declare a function that returns an object of type DNAT, which we will call chooseParent. But before we can do this, we actually need to know the sum of all the fitnesses of our individuals in the population. So let's just declare a variable of type float that will be called fitnessSum. And in order to calculate this, we just need to come here to our calculateFitness function, start it out at 0, and every time we calculate the fitness of one individual, we will simply add it to the sum. And now that we have this, we just need to generate a random number using the nextDouble function, and we will multiply it by the sum of our fitnesses. We'll then iterate through our population, and if the random number we generated is smaller than the fitness of the individual we are going through, then we will return this individual. Otherwise, we will subtract the fitness of that individual to our random number. If after all of this we still didn't get any individuals of our population, we will just return null. Now we can actually use this function in order to correctly select our parents for the crossover. Okay, so the essential part is done, but I just want to add a few more details. For convenience, we are going to add the fitness of the best individual of the previous generation, which we will call best fitness, and we will also keep his genes, which I will call best genes. Now, when we are calculating our fitness, we will need to copy the values of the best individual to those variables. And the reason we actually need to copy those values and not simply reference that individual by his index is because that individual was in the population array, which is replaced by the new population that we create. So when we try to access that individual, it will no longer be there. Okay, so let's actually find the best individual in our population. We will need to declare a temporary variable of type DNA, which will be the best individual, and we will initialize it to the first element in the population. So every time we calculate the fitness of one individual, we will check it to see if his fitness is better than what we had previously considered to be the best, and if it is, we will simply replace the best with the new best. After we complete this function, we will assign the best fitness variable to the fitness of the best individual, and we will copy the genes of that best individual to the best genes variable using the copy_to method, which is a C# function that simply copies an array to another starting at a certain index. In this case, we want to copy the whole thing, so we start at 0. Alright folks, so that's all for the implementation of the algorithm itself. Join us in the next video where we will be seeing the fitness function, the getRandomGene function, and showing the algorithm in action. Thank you for watching, and goodbye!